Good afternoon, everyone. Welcome to the problem solving session for Introduction to Semiconductor Devices NOC 23E82. This is week 12 on October 14, 2023. My name is Amit. I am a PhD scholar at IISc Bangalore. Just a quick summary. So we started with the material classification based on their conductivities, and then we delved into a bit of quantum mechanics. We saw the basics of de Broglie wavelength, which can be denoted as Planck's constant over the momentum, and the Heisenberg uncertainty principle. Finally, then we saw the quantum wells. So a quantum well is essentially your potential on the y-axis and position on the x-axis, and we saw something like this. Infinite wells means this potential is infinity, and any particle which is here will become trapped. It cannot escape this infinite well, right? And here the energies will become quantized, which is quite different what we encounter in the classical world, where we see that energies are a continuum. Then this is a asymmetric well from 0 to L. Symmetric well will be, let's say, from minus L by 2 to L by 2. Then we saw a unique principle of quantum tunneling, which is peculiar to the quantum world, so which is something like this. So again, your y-axis is your potential and this is your position. This is some barrier, let's say V0, and so a particle is coming with some energy, let's say E1. Classically, we know that this can never cross this barrier because E1 is less than V0, but quantum mechanically, there's a finite probability of finding the particle here. And so this is primarily due to the fact that quantum world is probabilistic while classical world is deterministic. Then we combined all this information of the quantum mechanics into then we bring, let's say, two of the lattice atoms of silicon together. Then their orbitals overlap, and we saw what we generate is something called a band gap. So band gap, this is EC, there are states above this, and this is EV, there are states below this. However, this region, this energy cannot be occupied by any electron. That's why we call it a band gap. And then we also saw that we can excite an electron from conduction band to valence band to conduction band. And all this understanding of this quantum mechanics we expressed in terms of something called the effective mass, or m star. It was different for electrons and holes, and although you see EC and EV are flat, this is just an illustration. Actually, if we draw the EK diagram, which you'll again see today, so E is your energy, K is your wave vector, which is 2 pi by lambda. So what we see is that there is a curvature to, this is your EC, and let's say this is your EV. So the curvature that you see over here in this band gap, so these band gaps, you can see the Ronick-Pane model. This is in your lecture notes, or you can refer to the videos. So this is the dispersion relation, EK relation, and the curvature in the conduction valence band gave the effective mass for electrons and holes respectively. And we saw that we can dope a semiconductor, means we have a lattice of, let's say, silicon, right? And you can replace one of these silicon atoms with phosphorus, then it becomes p-type. If you replace silicon atom with let's say uh, um, boron, it becomes, sorry, phosphorus will become n-type, yeah, and boron, it will become p-type. So excess electrons and excess holes, right? And correspondingly the Fermi level will change. So intrinsic, this means without any doping, the Fermi level is right in between EF. If you dope it n-type, it shifts upwards. If you dope it p-type, the Fermi level shifts downwards. So these are the considerations that we saw. And then we saw the equilibrium concentration, the NC and NV. These were determined again using some density of states and whatnot, and we saw some nice expression for Ni in terms of NC and NV. We also saw the carrier concentration that depends on temperature. For instance, very low temperature, none of the dopants are ionized, so you have partial ionization, negligible ionization. Then you enter an extrinsic regime wherein your all the dopants have either given their electrons or accepted their electrons. If you increase the temperature, however, even further, you enter what is the intrinsic regime. That is when the inherent silicon or the semiconductor bonds will start to break, and you'll have a huge concentration of electron holes. Usually what we do is we operate most of the times in the extrinsic regime. That's where we have the most benefits of doping. Finally, we saw the doping need not be uniform, and so what we saw is a peculiarity of we can have sloping bands. And if you have sloping bands, please remember this is potential energy. So when you have a gradient of potential energy, this is electric field, you know, it's minus grad V. So always sloping bands will have an inherent electric field, built-in electric field. And when you have electric field, whether internally or externally, the carriers will move. While they'll move, because the drift velocity is something given as mu e. Mu is the mobility, e is the electric field. This Vd is the drift velocity. And the conductivity, we also saw that Ne mu e and so on. Drift is one thing when the carrier is moving due to the electric field. However, there is a concentration gradient. The electrons are high on one side and low concentration is low on the other side, and the electrons can diffuse from one side to another. And the total current will be contributed by diffusion as well as drift, both of them. And the mobility and diffusion are linked by something called the Einstein relation. Temperature is also there. However, if we deliberately disturb the equilibrium, that is, we inject some carriers, or we generate electron hole pairs by light, which we see that we can do, for instance in solar cell we saw in the last class, and they can recombine also, right, which we'll see today in case of LEDs, right? So all those things can happen when the semiconductor is not an equilibrium, and all of this is condensed into what is called the minority carrier diffusion equation, where we elaborate on the total flux of minority charge carriers as a function of all this drift, diffusion, generation, recombination, and we analyze this in terms of low level injection. That means that the carriers that we are injecting are not very high. If they are very high, then our assumptions will not be valid, which we had made. Finally, we saw the p-n junction. This I'm emphasizing. This will come again handy today, because we are going to talk about light emitting diodes, LEDs. We saw different flavors. So essentially, it's a p-n junction. We primarily saw the step p-n junction or the abrupt p-n junction, right? This is p-type. This is n-type. Another flavor which you saw in the last session was pin, right? P-type, intrinsic, and n-type. Okay, and this another which is most commonly used is pn plus. This means p is moderately doped and this side is highly doped. That's why this plus sign denotes high doping. And then we saw that so p has excess holes, this has very few holes, so holes will diffuse from left to right. Similarly, electrons will diffuse from right to left, but they leave behind is nothing but your charge carriers, the lattice. So these are immobile charge carriers, and you see a depletion region being formed. Depletion region being there is no mobile charge carriers here, and we can actually solve this. The solution to the Poisson's equation. And these are the quasi-neutral regions where we don't have the depletion regions. This is an approximation that we made. These are quasi-neutral, and the depletion approximation means there's an abrupt change here. So this is quasi-neutral, and here there is charge. And the terms that throughout the course you have heard this term depletion width, which is this peak electric field. I told you. So whenever there is you can see there is charge separation, there will be naturally be electric field, and this electric field used to peak here. And this is called the stored charge, but you see the negative and positive. And if there's an electric field, this is potential, which is called the built-in potential, and which we denoted in equilibrium using something like this. Sorry about this, I'll draw it again. So we saw that it was something like this. So this is, let's say, your EF at equilibrium, right? EC and EV, and that we can and if we this is at equilibrium. However, if you inject, and this was the built-in potential I was talking about. However, if you forward bias it, this means you P and N apply positive potential to P. This means the barrier will get lowered, carriers will be injected, and huge amount of current can flow. In the reverse bias, opposite will happen. This VBI will increase in this direction, and very few amount of carriers will flow. However, what you will form here is a widening of depletion region. This region will widen, right? And since there is a charge separation in space, this is also being modeled using a junction capacitance. Okay, and then we saw the second kind of device, which is the metal semiconductor junction, also known as the Schottky junction, where we saw that we have metal on one side and semiconductor on the other side, and how the Venn diagrams bend, and the key terms involve Schottky barrier height, and the built-in potential was again there, because the electrons will traverse from one side to other if the Fermi levels are not aligned, and depletion width, and all these concepts came to the picture. The only difference being here it was through diffusion and drift in p-n junctions. In Schottky junction it's a thermionic emission, and which we also saw research as constant, and its comparison with the p-n junction. The key thing of this Schottky junction is it's faster, right? And we also saw that if you want to form ohmic contacts with a metal with a semiconductor and metal, you need to rely on Schottky contacts, because you need to have efficient transport of electrons from one side to another. Finally, we saw the heart of this course, which is the MOS capacitor, and we saw the 4 regimes in flat band, accumulation, depletion, and inversion. Just to clarify again, so this is your metal pad, which we say apply some potential Vg. This is some oxide. If it's silicon, usually it's silicon oxide, and here is your semiconductor. So metal, oxide, and semiconductor. This is a capacitor. The other terminal can be on the semiconductor itself. Let's say this is the other terminal, which we usually ground. This is also known as the body, by the way. So we saw 4 regimes. So depending on the value of Vg, the bands of metal and semiconductor can be flat. They can be accumulation, depletion, and inversion. We saw something of very important principle of the strong inversion. That is what I'll just summarize it in the sense that that usually what happens is that what we have is the body is p-type. However, if you apply a negative potential, right, so if you apply positive potential, you will repel the holes in, so you will repel the holes, you will form something called a depletion region. If you apply an even higher potential at the gate, the metal gate, so again metal, oxide, and semiconductor, this is how the diagram looks like. This is the metal. I'm applying the potential here. If you apply even a more positive potential, what's going to happen is that the electrons will now start get accumulating here. They'll start collecting here, and you will form a layer of electrons here. So strong inversion is when, even though your bulk is p-type, your this interface, oxide semiconductor interface, has turned n-type. That's why it's called inversion, right? And the key terms were surface potential, that is the potential that we encounter, and the voltage drop across. So this is oxide, this is a capacitor, ideal capacitor. Some voltage will definitely drop here. And then we saw the CV characteristic, capacitance voltage, so it's used to look something like this, CV. So this is your accumulation region, then your flat band when you cross V equal to 0, then your depletion region, and in the when you apply a even higher potential, so this is used to be VTH. If apply even higher potential, this is what we used to call low frequency CV, and the bottom curve is high frequency CV. And this difference arose because the charge carriers cannot respond fast enough to the change in Vg, right? Yeah, so that's that. And then we saw some non-idealities, that is the metal semiconductor work function can differ, they need not be the same, and some oxide need not be ideal, they can be trapped charges, and we see that the threshold voltage can shift accordingly. This voltage that you see, the onset of strong inverter essentially changes. So that's what we are talking about there. Finally, we saw an application of MOSFET, which is the MOSFET, the two flavors, the depletion and enhancement. So just to be very clear, so this is your metal, or the gate metal, which we used to call. Then you have your oxide, then you have a semiconductor as before. Just now there are 2 more terminals. So this is a p-type, so this is the body, we usually ground this, and this is your source terminal, this is your drain terminal. So again, if you invert this, you can form a sheet charge here between these 2 regions, and if you apply a potential between say source and drain, there can be a flow of electrons. And we saw that there are 3 regimes: the linear regime, the square law, and the saturation. We analyze these 3 regimes. For instance, the square law was through gradual channel approximation, and saturation we saw the channel pinch off. So essentially channel is not rectangular, channel is something called a tapered, something like this, and the channel can get pinched off, and you have the onset of saturation. We also saw the effect of if you don't ground this, right, you can have the body bias and the sub-threshold swing, that is the current does not magically start from 0. If you plot in logarithmic scale, you see there is a swing, right, which we if you recall 16 millivolts per decade at room temperature. That's what we had calculated. Finally, the MOSFET scaling, the Moore's law, that every 2 years number of transistors will double, and that the scaling proposed by Dennard. We saw the issues with short channel MOSFET, primarily that the velocity will saturate early, because will cause the early saturation of current, right? And then we saw linked to that was that the gate voltage is the drain current, right, is not Vg squared as in long channel. It is rather Vg, directly proportional to Vg, the linear dependence. And we saw the channel length modulation. So we modified the expression for IDS with this expression 1 plus lambda VDS. The rest remain the same, mu n Cox W by 2L Vg minus Vth whole squared. And then we saw briefly touched upon the new technology like high K dielectric to avoid the tunneling through the gate, and the FinFETs to have more control and lesser leakage. Finally, in the last session, we had talked about some optoelectronic devices where we saw electron hole generation by photons and the difference between direct and indirect band gaps. We'll discuss about this today. The two devices we talked about, the solar cell which operates in photovoltaic mode. We saw what do we mean by dark current, open circuit voltage, short circuit current. Fill factor is very important. There's an L missing here. Fill factor was very important. And then we saw the maximum power, how we can derive, and the efficiency of a solar cell, which if you recall the efficiencies that we typically get is 20 to 25% is it's a very efficient device in the market that we know of. Photodiode is basically you can sense it for detectors as sensors, which works on photoconduction. Again, the similar principle is that only thing that this fellow operates in the third quadrant of what? If you draw the IV characteristics. So here if you are operating your photoconduction, your photodiodes operate here, solar cell operates here, and today we'll see the LED operates here. And the key term again here was responsivity. Just like here it was fill factor, here is responsivity, which is dependent on the efficiency. So that is all from the previous session. So now we'll start for today's. I hope you've seen the lecture video. So what we are going to talk about today are two devices primarily, that is light emitting diodes and the lasers. These are also optoelectronic devices, just like in the last class we had solar cell and your I'm forgetting the other one, photodiodes. Yeah. So let's start with this. This is a very simple problem to start with. So it asks, in the context of radiative processes, semiconductors can be modeled as. So radiative, you can clearly see, comes from the word radiation. So radiation, what we're talking about is that the influence of radiation, here we mean light, so photon. How a photon influences a semiconductor. So you know that semiconductor, we have been writing the semiconductor as something like this, EC and EV with a band gap of EG. This is, we talked about this in the very first session, that how the you bring the atoms close together, they overlap, and the Ronick-Paddy model and the periodic potential and all that gives rise to this band gap EG. So these states, there are states available here for electrons to fill. Similarly, there are states available here for electrons to fill. So when we shine a photon here, so many things can happen, right? The electron can just go undetected, for instance. However, and photon, can go undetected. It will not interact. However, if the energy is high enough, a photon can excite the electron from here to here, let's say, or electron from here to here. And if the energy is low enough, let's say energy is only enough to excite this much, but there is no state available, so this is not acceptable. So there are different ways in which a radiation or a photon can interact with our semiconductor, right? So as you can see here, the two levels, in this diagram it's very easy to see there are two levels with which we have. This is the top level and this is the bottom level. So this is a very simplistic model that how is radiation going to interact. So we have only two levels, the top and bottom level. Radiation, the transition of electrons can happen only between these two levels. I emphasize this is a very simplistic model. So however, there are many things like traps and defects, right, which are present in our devices. So what they introduce is, which I'll show it in a different color, the traps or defects. What they introduce is, they introduce some energy states here. It's forbidden, right? But it's for an ideal semiconductor. For a non-ideal semiconductor, it can introduce some trap states here and here. So what can happen is that even for an photon with energy lower than Eg, it may excite an electron here, right? It can absorb this Eg, whatever it is, Eg by 2, Eg by 3, whatever it is. So this can happen, but we are not for starters, we are not talking about these systems, so we'll ignore the traps and defects for now. So what we are left with essentially is a two-level system. This is the first, this is the second. Another thing that I'm ignoring, the states that are present here. I told you the states are present here and here. So what usually happens is that every entity will like to get to its lowest energy state. So even if electron is here, right, it will dissipate its energy by whatever means, by phonons or whatever means, and it will try to come to this state, right? Similarly, if a hole is here, it will dissipate its energy by whatever means, it will try to come to this state. Note hole energy increases in this direction. Okay, so if whole energy, if I denote a hole moving something like this, means energy is decreasing. Similarly, an electron energy is increasing in the vertically upwards direction. Okay, so if an electron comes, by some reason it's here, it can lose its energy, come to the lowest possible state, which is here. Hence we denote it only by a two level system, although there are different levels, multiple levels available, right? Density of states clearly illustrates that there are multiple levels that are available, right? But we are not concerned about that in this case, right? Just consider only two level systems. Thus a semiconductor, when interacting with radiation, can just be simplified to a two level system, with the two levels being EC and EV, and that's all. We do this and we'll be fine, nothing else to do. Okay, and this is the basis of all our analysis for today. This very simple understanding that a semiconductor can be reduced to a two level system. This will be our basis of understanding of all the of this session rather. Okay, right. So the second question for today is that what are the fundamental radiative processes proposed by Einstein? So this was done by early 19th century by Einstein himself, where he proposed this two level system. By the way, this two level system is not restricted just to semiconductors. So this is a course of semiconductor devices, hence we are discussing that. So when you talk to for instance in these states can exist. So I'm talking about this, that the two level systems, they exist not only for semiconductors but for various other devices. For instance, these molecular levels, they are also different. So for instance, if you have your friends from physics background, they talk about this atomic levels and molecular levels, the splitting happens. So there also they can be molecular atomic levels, not just the electronic energy states that we are talking about. So there also we model use it two level systems. It's a very comprehensive understanding, comprehensive field. It spans many fields, and the basis of it remains the same, that there are two level systems. And when we shine light, right, how it behaves is what we are talking about here. So here the fundamental radiative processes are the three, actually two: absorption and emission, but we have split the emission into two parts for our purpose. So absorption is very simple. So this is your h cut omega or h nu, however you move. So let's say an electron is here. So if this energy is greater than or equal to Eg, which is the band gap here, you can simply absorb the electron. We have seen this multiple times now. So for h cut omega greater than or equal to Eg, you will have something called the absorption. Second thing can happen is that, note that at any temperature greater than room temperature, 0 Kelvin, the electrons will be here. Their amount may be very small, but some of them will still be here. Now what can happen is that, and this is excited state for electron, if there is a hole available here, what can happen, this electron can now drop down to this hole and we'll have an electron hole recombination. Here it was electron hole generation, here it's a recombination process, and while in the process of recombining, so again this h cut omega will be equal to Eg. Again please note that I'm not considering the any states which are above Ec or below Ev. So that's an assumption that I'm making. This we call is spontaneous emission. Why spontaneous? It will happen on its own. It doesn't require any external stimulus. If we have electrons here and holes here, this process will naturally occur. You don't have to force it to do it. A cousin for spontaneous emission is the stimulated emission. So what happens is that, as the word suggests, you're stimulating this material. So again, the same system, the electrons are here and there are holes here. Okay, so what can happen, you're shining this light again of the same h cross omega equal to Eg. You're shining this light, and when you're shining this light, what happens is that this electron will fall from here to here, and again this will generate its own h cut omega. Again h cut omega is equal to Eg, the band gap of this semiconductor, and this first radiation comes as it is. So you'll see what's happening to this is actually there's more physics involved behind this, but you can understand is that this is acting like a catalyst. Like in chemistry, you must have studied high school chemistry, there's something called catalyst. They do not get consumed in the reaction per se. So this is same thing. So this is coming, this is stimulating this, and it comes out as it is. Now the key things to note here is that the frequency of them will be the same, as well as the phase. So please, how does this come into the picture? Please remember that light is an electromagnetic wave, I should say, right? So there you have the phase component. So if I can write the expression, you must have heard something like you must have read something like the exponential ikx minus omega t plus phi. Just don't get worried about this if you have not heard or read about this. Is the electric field that I'm writing. This phi is the phase. So every photon can have its different phase. Here it's not the same. They have the same phase, or this word you must have heard, coherent. It is a coherent light source. Two photons. These two photons are coherent in case of a stimulated emission. Okay, right? So we see that the fundamental radiative processes that were proposed by Einstein are these three: absorption, spontaneous emission, and stimulated emission. So this will be the correct option.
Now, sir,
Yeah,
I have been putting stimulated emission.
yeah, go ahead.
So, because we are shining the light, it isn't inefficiency, right? We are shining the light, and there is only one radiation coming out. Then how it is efficiency?
Okay, so talking about, I'm assuming you're talking about the case of stimulated emission, right?
Yeah. In stimulated emission, we are shining a photon of H
Yes.
omega,
Yeah.
and then we are in return we are getting two photons, right?
Yes, correct.
But initially we are spending one photon to get two photon, like
Yes.
like
Yes. That
so
you are.
how it is happening actually. So initially one is coming, then how it is getting to.
So okay, so I'll try to explain to the extent I understand this. So what
Okay.
happens is that what you are seeing here is just these two energy levels, right? So I'll draw
Okay.
it for you.
Yeah.
So you are seeing this EC and you are seeing this EV. Actually, and you're seeing that this transition is happening, which is generating this other h cross omega, right?
Okay.
This is what happens is this is not such a straightforward process. I mean to say it like this. Hold on a second. There's some problem with my marker. Yeah. So what happens is that there is an intermediate state also. So usually there is an intermediate state. That energy level usually might lie in between. Let's say it's lying in between.
But we don't have intermediate energy level, right?
No, we do not. So what I'm saying is that this is a transition level. So it's not stable. So what all the states that we are drawing here, for instance, the states that we are here, right? They are stable states. Means they can retain. So we'll introduce one more concept called the lifetime. So what I'm trying to say is that this is how this is modeled, is that there is some transition state. This is called a transition state. So
Okay.
in order to in by the use of this incident photon, this transition is accelerated. The probability of this transition gets increased. So it's not like that the electron is falling from here to here and then from here to here. No, this is I'm just that's why I'm saying it's not very intuitive here, that it looks like there's another state here. It's not. Just assume that there's a transition state. You are going from point A to point B, right? That's why I called this fellow as a catalyst. That's why I was calling it will not get consumed, but it will accelerate this process of emission of another photon of same frequency and phase. So there is a transition state that is involved there, which the probability of going through this transition state gets increased when you apply this this incident photon. That's what I'm meaning to say.
So it is transitioning from A to B, then B to C. So there is kind of two photons are coherent,
Yes,
right?
no. So that's what I'm saying. This energy level, I do not know where it is. This differs from system to system. There are some systems in which an electron, or let's say for instance an atom, can have this intermediate energy state. There are different devices, not just in semiconductors, in some other systems, that was molecular systems or atomic energies where we plot. So there, this system, this thing, stimulated emission occurs, similar thing. This is true only for semiconductors. We are concerned only about semiconductors here. I'm saying that usually there is a transition state that is involved, that gets the probability of going through. So it's not staying here. It's in fact a single process. Just for illustrative purposes that I'm drawing it here. This incoming photon helps this transition for an electron to drop from EC to EV. That's all this incoming photon is doing. That's why it survives. It doesn't. It's not getting consumed here.
Yeah.
Right. So these are the three processes, and that's why it's called stimulated emission, because this incoming photon that we see is stimulating the system to generate another photon of the same frequency and phase. Okay, which is missing in spontaneous. Spontaneous can occur on its own. It doesn't depend on the incoming photon. It happens on its own, in fact, regularly. But this stimulated emission needs an external stimulus. Okay, so what else do I have here? Okay, so there's something else. Let me just hold on a second. Right. So another way of seeing this is to luminous intensity is nothing but the intensity, the amount of light that is coming out essentially per centimeter square per unit area. This is for a gallium nitride, which is a semiconductor. Its band gap, it's around 3.4 eV. So what you're seeing here is that we see that as soon as the energy crosses the band gap, you'll have absorption, which we are seeing in this case. So this is happening, the dotted line that you see. This, the photoluminescence that you see, is what we are talking about of the spontaneous emission. So you see there is a peak that is coming. This will become more clear when we talk about the LEDs. Okay, so that's what I'm saying. This is experimental data, and we can see the same thing which you're talking about theory in this plot. All of this is from like your lecture notes. So all of this data that you see in today's session is from your lecture notes itself. Okay, now once we have established that these processes occur, now we like to know a bit more about the processes that are behind that, exactly what is happening, so to speak. All right, so that's what we talk about here now. Okay, so we have to choose the equation for spontaneous emission process. So let's just draw the spontaneous emission process, and what I'm going to do is that, so this is your high energy state. Let's call it this EC and EV. The lower state is EV, and what we are going to have here is that, let's assume that the concentration of electrons here is N2 at this level, and concentration of electrons here is N1. Okay, so what's going to happen now, we need to know that how much what is the rate, what is the rate of decay of, let's say, of N2, right? So that's why we write, so what we are interested in knowing is what is dN2 as a function of time. What is this? So one thing you can clearly see that it will depend on the amount of electrons that are present here. If there are fewer number of electrons present here, the decay will be slower naturally. So what we can clearly see is that dN2 by dt should be directly proportional to N2, not on N1. It will only depend on the electrons that are present here. Secondly, you will see that as the amount of electrons decrease, the rate will also decrease, because there are no fewer electrons to drop to the valence band. Hence what we do is we introduce a negative sign to denote that the concentration will decrease, times N2. So this will be my complete expression from your lecture notes. The same thing, the value of K is usually given by this Einstein constant of A21. So what does 21 denote? 2, the first symbol denotes from where you are coming. So we are coming from energy state E2. Let's call this E2, not EC, dV. Okay, this is E1. Where you are going is E1. And this A is just a symbol for denoting the spontaneous emission. So hence, so dN2 over dt should be equal to minus A21 times N2. So which will be this option. Okay. Someone has their mic unmuted. You have any question?
No, sir.
Okay. Right. So this is for spontaneous emission. Similar equation can be written for stimulated emission. Right. So let's do this. So this level is again E2. Bottom level is E1. Again we'll assume that N2 electrons reside here and N1 electrons reside here. So again we are interested in finding the decay of dN2, right? So as previously, you can, one thing you can clearly see, it will be directly proportional to, just like we saw there, N2, right? And second thing what we saw is that the rate will decrease as the amount will decrease. So again I'll put a negative sign, K and 2. Now we also have to take into account of this value. Okay, so this, we are denoting only one energy here, right? If we have many photons that are incident over here, so how do we denote that? So we denote it using something called spectral energy density. So I'm write Kn2, where this variable u as a function of nu, which is the frequency. So this is your frequency, right? So so omega, I guess, will be your 2 pi nu. Nu is your frequency. Okay, and again, just like the previous case, this K, which is the proportionality constant, is written as the Einstein coefficient B21. 21 again, 2, we are coming from 2, we are interested in going from 2 to 1, right? So 2 will come first and then 1, and rest of the terms we have talked about it over here, right? So the only difference from the spontaneous case is that now this will also depend on the incoming frequency, on the incoming frequency also, rather its distribution with respect to frequency. How much of the spectrum that is being so just assume that this piece of semiconductor is sitting in a sunlight, in sunlight, right, or in a room. So there are many frequencies of different intensities that are falling. If you recall, we did the solar spectrum the last time, AM 1.5, right, which used to look something like this. Sorry, not negative. So just ignore this. It used to look something like this, right? So here, so this was again the AM 1.5 plot that we have. Here we had I forget as lambda or energy. So we had seen this plot. So this function is essentially that. This is sunlight. You can artificially generate these functions. You can, for instance, turn on only red or green light, right? Then it will be different, and you can also control the intensity, how bright the light is. So you can all control all these things, and this is the function to denote that. Okay, so we have a rate of change of N2 will be minus B21 times N2. This is the option, minus B21. It will not depend on N1. It doesn't care how many states are available here, because it has to decay from here. So it only cares that how many states are available in the upper level, the N2 level. That's what we are doing here. Okay, now a key thing is that these the coefficients, the A and B, which we had talked about, are not independent. They are dependent on each other. So we had talked about the we talked about A21 and B21 both. So A21, remember, we'll write it here. A21 was your for spontaneous emission. B21 was for your stimulated emission. and we are required to find the relation between the two. This is from your lecture slide itself, so there's nothing, I mean, to explain much here. Just that we saw how these terms came into being. The only thing that I want to talk about is dN1 over dt. So again, this is the same logic. So we want to find the rate. It will depend on n1 and a negative dependence. If that, so n1 is the electrons, let's say here, n2 here, this is the energy state E2, this is the energy state E1. Okay, so so it will depend on n1, and it will also depend on your, again, spectral density. Why? Because if your h cut nu is less than your Eg, just imagine that case, then there cannot be any absorption, right? Hence, so that's what I was saying, this it's very powerful term in the sense this will dictate how the system will behave. The stimulus that you're providing is this. Only spontaneous emission does not contain that term, because it's self-sufficient in the sense that it only cares about the electrons that are present here in state E2, the high energy state, right? Hence you do not see the spectral energy density term coming in spontaneous emission. Okay, and it so turns out that these two constants, the emission constants, are related to each other. A21 and B21 are related to each other using this expression. The other key thing that I want to talk about here is, you see these terms G1 and G2, right? So G1 and G2, usually for here we have assumed that they are in our system, we have assumed G1 equal to G2 equal to 1. So you may have heard of this term degeneracy, but I like still to clarify that. How should I say this? Okay. So you remember the electronic energies, like let's say we say 1s2, 2p2, and 2p6. So this is your this will be your helium, and then neon, I guess, atomic number 10. I think it's neon. Correct me if I'm wrong. First is helium, I know. Third is argon. I think this is neon. Okay. So what's going to happen is that, so remember, we say these are the 6 orbitals that are here, and we assume their energies is the same. That's a degeneracy. So actually the wave functions are different for each of them. The functions are different, but their energy is the same. So that's the degeneracy. So when a system, it just happens that it has different wave functions or different formulations, let's say, but its energy is the same. So just think of it like this, that 1 plus 4 is also 5, 2 plus 3 is also 5, 3 plus 2 is 5, and 4 plus 1 is 5. So essentially what you're seeing, the total energy is 5. There are two entities here. First has energy 1 unit, second 4 unit. So it has 4 degenerate states. Right? I did not write 0 plus 5, and I'm using only integers just for this is an illustration. What do we mean by degeneracy? How to understand it in very simple terms. This is how we understand. It can have different combinations, right? That's what combinations is, just the wave function that I'm talking about. But the total energy of the system is the same, which is the 5 units here. So this is what we talk about. So in complex systems, more often than not, degeneracy arises, right? So this is what we are. So here it's a very simple case. We just assume that E1, it's only one. It's not more than one. There's just only a single energy state of energy E1, similarly single energy state of energy E2, and that's it, right? But this is not the actual case. This is more a general thing. For as far as this question is concerned, so A and D are related using this expression. Which one is it? 8 pi A. Yeah, so this option. Okay, so yeah, that's it for I think, yeah. So we are done with the basics of the emission and absorption. Right now I'll pause a bit here. If you have any doubts or comments, please feel free to ask. I'll be more than happy to answer. Oh, and before I forget, although it's supposed to be the last class today, next week there'll be a 1 hour session. So I was planning for a revision, but if you have any specific doubts or concepts you want to be revised, I'm afraid I do not know the dates of your exams, right? But if you want, so tomorrow, next week, same time, just 1 hour session, 3 to 4. So if you have any specific doubts or concepts you want to discuss in the class itself, please email me. I'll share my email address. Um, you can check your chat box. Just drop an email with your doubts or the name of concepts that you want to be discussed in the class, and I'll see what I can do. If there are more than if currently I can see only 4 to 5 people in the session. If there are multiple responses, that I'll try to create a flow so that I can cover most of the topics. If there are very few or no responses, then I'll try to see what I can do. So my preference is personally MOSCAP and maybe PN junctions, because these are the very basics of the course. So if you want any specific doubts, even numericals is fine, as long as they're not from the assignment which is due. I'll be more than happy to discuss. So just share or just write on the email address that I have shared. Okay, now we come to the second topic for today, which is the light emitting diodes. Okay, this is spelling mistake, it become diodes. It's diodes. So what we have here is essentially, this is just a PN junction, which is forward bias. So all the things that that I talked about in when I was going through the summary of previous session of week 4 and week 5, so all those concepts will just come back again here. So you can see this is a forward bias diode. How do we see that? How do you say we can see? You can see this arrow. This means a current is flowing. But still, what is the best indicator is you can see the Fermi level is split. This is EF of N. Fermi level on N side, quasi Fermi level. This EC and EV are already noted, and this is your EF of P, quasi Fermi level on the P side, right? And you can clearly see the this has shifted a bit upwards. So the VBI has reduced. So VBI effective is essentially only this now. VBI minus V applied, I should say. We have applied some positive bias to that. So this is a forward bias PN junction. That's why I was telling that when for light emitting diodes, we operate in the first quadrant. Solar cells, we saw we were in the fourth quadrant, the photovoltaic mode, and photodiodes, we saw we were in the third quadrant, the photoconductive mode. Second quadrant, I have not seen much use of it, but there are some devices, some exotic devices which work even in the second quadrant. Okay, so we have this light emitting diode is nothing but, very simply, is a PN junction forward bias PN junction, right? The only thing that is happening is that currents, what we are doing, we are injecting some currents to the battery, correct? So what we are doing is that we have a huge supply of electrons in the conduction band, right? And what's happening is that they are going to drop over here to recombine with the hole. So this is essentially based on recombination of electrons and holes. So in the last session, if you recall, we were talking about some device which convert the from one form of energy to the other, right? We were discussing this, that solar cell, what does it, converts light energy to electrical energy. I talked about leaves, the photosynthesis process which they carry out. They convert light energy into chemical energy. This device, light emitting diode, as you can clearly see from the name, converts it. The output is light energy, and the input, what we do, because we are applying a bias, remember, forward bias. So the input that we have is electrical energy, and the output is nothing but light energy. So that's what it's doing. So how will the light come about? You see this photon using the through the process of spontaneous emission, this photon will be emitted. What will be the wavelength of the photon, or the h nu? So h nu will be equal to Eg, the band gap of the semiconductor. Okay, it's very straightforward, very good. What kind of a materials can we choose for this? So remember that we had talked about the direct and indirect band gap in the earlier sessions also, and I think in the last session also. Again, I'll talk about it here. So what we have here, first I'm drawing the direct band gap. So this is your EK diagram, energy versus K, the wave vector. So this is your EK, this is your EC, and your EV. So what you can clearly see is that the top of the valence band is coinciding with the bottom of your conduction band. This is the example of a direct band gap. Now I'll draw an electron and see how it behaves. So we have an electron here, let's say lying at the bottom of the conduction band, and it has to travel in this direction to come here. And in the process, it will emit a photon of energy h nu, which will be going to equal to the band diagram Eg. Straightforward process. So an electron, if it's available here and if there's a hole available here, it can drop down, can recombine, and in the process it will emit a photon of energy Eg. Let's do the same analysis for an indirect band gap material. Again, EK, the dispersion relation. So let's draw the valence band. So this is your indirect band gap. Okay, and what we have here is something like this. This is your EC, this is your EV. So now what you can, again I will try to do the same process. An electron is here at the bottom of the conduction band, and it has to come here now. So again, in the process it has to give away this energy Eg. So what's going to happen, a photon should be generated, but it also has to traverse this. Momentum also has to change. This K is also the momentum. Please recall that the wave vector 2 pi by lambda is related to momentum. So momentum also has to shift. So in this case, this means conservation of momentum has to be there, of momentum and energy. Actually, it's true for both the cases. Here the momentum is conserved by the fact that the nature has given some materials this property that their band gaps align, the wave vectors align, at which the maxima of valence aligns with the minima of conduction. So their phonon is not required. Momentum is naturally balanced. Only the energy conservation we have to do. Here we have to conserve momentum as well as energy. So here this means what we need is also a phonon, nothing but for momentum conservation, and a photon for energy conservation. So here it's a 3-particle system, an electron, a photon, and a phonon. Here it's just a photon and an electron. As it turns out, these processes are inefficient, much inefficient as compared to direct band gap transitions. Hence what we see, the materials for LEDs that we see are direct band gap, like gallium arsenide or gallium nitride. For more details, I recall that in the lectures, Professor Naresh has presented a slide which showed the evolution of direct band gap based LEDs. So it's a very good, and you can understand after 90s how nitride semiconductors grew, and the Nobel Prize was also awarded in the past decade for the invention of blue LED. So that's the complete picture, by the way, of the theoretical aspect, at least the basic understanding of a light emitting diode. Okay, right. So now so equipped with this knowledge, what we'll do is we'll try to solve some problems, and this is just a theoretical part again. So I'll just keep introducing a few other related concepts of the LEDs itself. So let's see this problem now. So the question says that the radiative and non-radiative lifetimes of an emitter material are given by tau r and tau nr respectively. We'll see what these terms mean. In which of the following cases will the material be an efficient light emitter? So in this case, I had talked about that. So when an electron will recombine with a hole, a photon will be generated. Correct? There are other processes also through which this electron can come here. There are many other processes, in fact. So as I was saying, there can be trap states. If there's a trap state here, electron will come from here, and then it can come from here. There can be multiple phonons. It can dissipate its heat, its energy in form of to phonons itself, to multiple phonons, and the electron will reach here. It will lose its energy, and overall there will not change in momentum, right? So that's what we mean by radiative and non-radiative. Okay, so we'll denote it like this. So this is the excited state, or what we have been saying as EC. This is your EV or the ground state. So we want, for instance, we are talking about this and this electron to come here, right? And you can see the electrons are being injected. So this is similar to your forward bias PN junction, which is the case for LEDs, the operation for LEDs. So here, just consider only these two electrons here. The right electron, which is coming, which is going to recombine with the hole, the right hole, and in the process it will generate a photon. This process is known as radiative recombination, because it's recombining and a radiation is coming out. I told you this electron can recombine with this hole through some other means. There can be traps in the lattice. It can combine through a phonons. There are many other processes, right, through which this process can happen, and these processes usually will not give a radiation. So no light will be emitted from this. But please understand, we are injecting some amount of electrons, and ideally what we expect is all of these electrons to combine with the hole radiatively. This means because you want the maximum amount of photons coming out of a light, coming out of your LED bulb, right? You want that. So what we do is this: we expect all the electrons that we are injecting to recombine radiatively with the holes. Okay, that's our aim. That's the best. That's the ideal scenario. Efficiency of 100%. Okay, let's do it now mathematically a bit. So this R is your recombination rate, right? And this R stands, small r subscript stands for radiative, and it will depend naturally on the amount of electrons that you are injecting, the excess electrons delta n in this case, over the radiative lifetime, that how much time. So everything that is happening will take a certain amount of time. This is not a spontaneous, it's a spontaneous emission, but that spontaneous means that it's unassisted, it has no stimulus, but it will take some certain time. This whole process takes certain time, and hence the rate will naturally be divided by time. The flux, that the amount of electrons that we are providing over the time it takes to recombine radiatively. Similarly, non-radiative recombination rate will be the amount of electrons that we have divided by the time it takes to recombine radiatively. It will be the total recombination rate. It will be a summation for both. This is very similar to when we did, remember, at minority carrier diffusion equation, where we were writing G minus R, generation minus recombination. Here there are two flavors of recombination, hence they will combine, right? Okay, and thus the total recombination rate can be given by this expression, delta n by tau. So if you put these values here, right, if you put the r and r nr here, so you can clearly see 1 over tau will come out to be 1 over tau r plus 1 over tau nr. This is so when we measure, for instance, experimentally, it may be difficult to decouple these two. What you can measure is this, the total recombination rate. Okay, and this radiation rate can still be measured in the sense that you have this, you can measure the intensity, for instance. Then you can have an idea of radiative recombination rate. So that's an experimental thing, but from our aspect, this is the picture, right? What is the efficiency? The efficiency we want is R by R. So R is the total recombination rate, it's noted by this, divided by, in the numerator we have the radiative recombination given by this expression. By the way, this, so let me just first write the expression. So delta n by tau R divided by delta n by tau. This will come out to be tau by tau R. So if you just take the LCM over here, so this will come out to be tau R, tau nr for tau r plus tau nr. This is divided by tau r. So what you can get here is tau nr. So this is the efficiency that we are getting here. It depends on the, naturally, which you must come to expect, it depends on the uh, the lifetimes of the emitter material. This means these electrons, whether they're going through non-radiative route or through radiative route, right? So we want it to be as efficient as possible, right? So what we want is that we want for high efficiency, I'll write it here, for high efficiency, let's say we make eta equal to 1, the most efficient that is possible, right? So when we do that, so we'll get tau and r equal to all right, or let me do it this way. Let's not do it this way, let's try to do it through limits, because then only we'll be able to appreciate the relative lifetimes. Okay, eta should approach to 1, right? So this means tau nr should approach to 1. I'll divide, what I'll do is I'll divide numerator and denominator both by tau nr. So it will be tau by tau nr plus 1. This should approach 1. So this will approach 1 only when this term is very small, because if this term is large, let's say this term is 10, this should be 10 plus 1 11, 1 by 11, this will be around 0.9. So what we want is that this implies tau r by tau nr should be less than 1, then only the efficiency will increase. So this will give me tau r should be less than tau nr. What this means is that this lifetime should be very small. This means an electron, if it's traveling through this path, this should not take, this should be very small. Let's say if this is microseconds, if this is, let's say, nanoseconds, this should be microseconds, right? There has to be huge difference between their lifetimes. So what we get is tau r should be less than tau nr, this one. Just simple mathematics and nothing else. No, so we just, in this problem, we just identified the two routes through which the recombination can happen and how are their lifetimes related. And this thing I was talking about, this fellow is also known as internal quantum efficiency. This essentially tells you that of all the electrons that you are injecting, how many or what percentage of them, note this formula, recombination through radiative means, how many of them are taking this route, the radiation route, and so if the more it's closer, the more it's taking the radiation route, the higher will be the efficiency. This is the internal quantum efficiency, right? That how many percentage of electrons are being converted, their energy is being converted to light energy. The other aspect of this is external quantum efficiency. We have just talked about the internal quantum efficiency, so let's finish that. So what we have is IQE is number of carriers injected, right? We are injecting some carriers, so that's in the denominator, the number of carriers injected, and the numerator will be number of photons generated. This some extraction is different, okay, so which we see here. This is the p-n junction, so the radiation region, you are generating some photons. Not all photons will come out. You can see this photon is coming out, right? Let's call this p1, let's say. This second photon is not, this is traveling in this direction. This third photon p3 is going here, and if you have a reflective coating on the back, it can come out, it may come out, right? So here the photons can go in different directions, so just because they are generated. So remember, p1, p2, p3 are generated. P1 is the one that is extracted. Both of these things are important. You have to generate first. That will be determined by internal quantum efficiency. So that will be, you are injecting some carriers. Remember, we are converting electrical energy to light energy. So we are injecting some carriers and we are generating some photons. So that is your internal quantum efficiency, generated over injected, this fellow. Okay, this is true for internal quantum efficiency. However, how many photons are you able to extract out of the generated ones? That's your external quantum efficiency. So this will be extracted. How many are coming out of this device? That these are the only things that you see from your LED bulbs, divided by generated, right? So this one, hence this option C is correct for this problem. These so this is the theoretical aspect that we're seeing. Lot of research and development goes into this to choose the materials for which have high IQE, to choose the coatings, the reflective coatings, such that the EQE increases, right? There are many things that the device architecture, there are many things that go behind this. We are just touching the surface of it, right? And one other close related concept is this reflection. So you see, if it's sitting in air, let's say this is air here, and this material, let's say, has refractive index n2 and air has n1, right? So how much of it will get reflected and how much it will not, this is given by this expression, right? So the refractive indices also matter, and reflective indices we'll see later will depend, and they depend on the band gap, right? Band gap of the material. So also choosing the material also becomes very important in this case, right? So these are refractive indices. Can call this reflected flux, you can call it, okay, of photons. So whatever are generated, how many of them are able to escape this interface to the air, okay. So that completes some of the things about LEDs. Now the next things, this is the next problem that we have. This is essentially summarizes the LEDs that we had talked about, right? So what we have is that for the multiple choice question with more than one correct answer. So gate asks these type of questions. Unless you select all the correct ones, you'll not get awarded. Usually there is no negative marking here in the competitive exams. So but it's a scoring thing, because their marks are usually higher per question. Okay, so we have seen that photon generation is dominated by spontaneous emission. It's not stimulated. We're not shining any light. The stimulus is not light, but stimulus in fact is your electrical injection, right? So this is the correct option, one of the correct options. Let's see what about others. They are incoherent sources or they are coherent sources. They are incoherent sources. Why incoherent? We have talked about that for them to be coherent, they have to be stimulated emission, which is not the case here, because the spontaneous emission, they are incoherent sources. Thirdly, the point whether they are monochromatic or polychromatic. Monochromatic means one wavelength. Polychromatic means more than one wavelength. For instance, sunlight or white light. Let's say white light is brought up of which you have read is 7 colors, right? Those 7 wavelengths. So when you talk about whether the LEDs are monochromatic or polychromatic, it turns out, although when we say blue LED, green LED, it's not pure blue and pure green. So how do we know that? Because we have something called FWHM, full width at half maximum. What does it mean? You draw the luminous intensity versus the energy, right? This is the peak that we get here. You can clearly see it's only after EG that you are getting, which makes sense, because below EG there will be no, the electron has to travel from conduction band to valence band, so energy has to be EG at least. Hence you see below EG there is nothing, correct. Secondly, the density of states in the conduction band goes at square root of E. You see this dependence 1/2, it goes as square root of E. The density of states, DOS, which we write, goes as square root 1/square root of E. This is for 3D system, which is the case in this. This is the case here. And density of states we already talked about, I think, in the second session. You can go through. We did not talk about in the session, but in the lecture there is a passing reference to that. Okay, yeah. Finally, but the other curve that we have is Boltzmann distribution, and it drops as, so what is written here is exponential of minus e over kt, which we know the Boltzmann distribution drops something like this. And so the total energy will be simply a product of these two, which we get this kind of a curve. So this is the peak that we get. So let's say whatever this peak value is, let's say I naught, at I naught by 2, which is this value, whatever the width is, we call it full width at half maxima. This is half maxima, I naught by 2. Whatever this width is, this line is called F2HM. It turns out depends on the temperature. The value is 1.8 kT, and you can clearly see this is not monochromatic. You have this wavelength, this wavelength, this wavelength, this wavelength, this wavelength, this wavelength. This is a theoretical emission spectrum. When you have idealities, more absorption will come into the picture, but at least theoretically we can see it has multiple wavelengths. Hence we can say they are polychromatic sources. I'll again emphasize that even though we say it's blue LED or green LED, it's not a single wavelength. This means it has spread, which you see over here, 1.8 kT. We can quantify that actually. So kT is, let's say at room temperature, is 26 MeV. Right, let me get my calculator. We'll see how much it turns out to be. So 26 times 1.8, that is around 47. So this is around 47 milli electron volts. Okay, so the wider the delta E is, the more spread you have over here. All right. Okay, so now we have talked about the basics of LEDs. Now we'll just quickly solve some problems. These are more to tickle your mind rather than your pen and paper calculations. Okay, so consider the IV characteristics of various diodes made up of different materials as shown in the figure. So you can see again this is the first quadrant that I was talking about. So we have different materials, so germanium, silicon, gallium arsenide, phosphide, gallium indium nitride, and so on. And we are operating at a room temperature, about room temperature. And they also said that their Eg increases, which is evident from their the knee voltages, right? This is the forward bias characteristics. Okay, statement 1: LEDs made from silicon and germanium are efficient as their thresholds are less. You can see the thresholds are less, so this is around 0.5, yeah, something around 0.5, and this is around maybe 0.7 or something, right? So they are efficient as their thresholds are less. No, because remember, thresholds depend on IQE, internal quantum efficiency, right? And we know that internal quantum efficiency are, again, then they depend on spontaneous emission and radiative recombination rates. Remember that expression? Eta we wrote R by capital R just a few slides back. This is what we wrote. This was spontaneous emission, and we know that this happens for direct bandgap materials. In indirect, it's very inefficient. In silicon and germanium, the elemental semiconductors are indirect bandgap. So the LEDs are not efficient. This is false. Statement 1 is false. And thus it's linked to second statement. Silicon germanium diodes cannot emit light. Yes, very inefficient. It's not. So this is true. And the reason it is true is that they are indirect bandgap materials. Silicon and germanium are indirect bandgap materials. So what we have is S3 is false, so this option is incorrect. Sorry, S1 is false, so this option is incorrect. S2 says is false. No, S2 is true. This option is also incorrect. Only statements S2 and S3 are true, correct, and S3 is a correct explanation of S2. Yeah, so this is the correct option. Let's check other. S1, S2, S3 are true. No, S1 is false. S1 is false, and S2 and S3 are false. No, this is incorrect. So we have only S2 and S3 are true, and S3 is the correct explanation of S2. Again, because silicon and germanium are indirect bandgap materials, they will not emit light efficiently, and thus we do not make LEDs out of silicon and germanium. We make them out of gallium arsenide or gallium nitride, all right, or their alloys. So for instance, this is ternary semiconductor, gallium indium nitride. Okay, all right. So this is the second problem related to this, is that so this was the first problem that we saw. We have solved this. So this was true, this was true, and this was false. Right. Problem 8. Choose the correct statement with respect to frequency of light emitted. So we know that this is very straightforward again. So we know we are considering only two level systems, and sorry, 1 second. So I have EC here, I have EV here, and the light will be emitted when an electron drops from here to here. And I know that h nu, the light frequency that is emitted, should be equal to Eg, the band gap, right? So now we need to, so now if we increase, so we know that Eg, it's given, of gallium indium nitride is greater than Eg of gallium arsenide phosphide is greater than Eg of gallium arsenide. The rest two we don't even write because they'll not emit light. We've already established that they cannot emit light. Okay, so H will get cancelled, so I'll write H nu of gallium indium nitride should be greater than H nu of this greater than, sorry, H nu of gallium arsenide. H will get cancelled, and what will remain is that the frequency of gallium indium nitride, the emitted photon with this frequency, will be greater than for gallium arsenic phosphide, and which is greater than gallium arsenide. So what we'll have is this one. Gallium arsenide will be less than arsenic phosphide and then indium nitride, right? This is the correct option. This is directly dependent only on the band gap, because we are considering an ideal two level system where with no idealities, no traps, and so on. Okay, so this is a very straightforward system. Okay, so that's about so this is for this set of problems, where in these set of problems, just a second, why not option C? Okay, you tell me. We have already established that this is true, this is also true, this is false. In the first part we saw that silicon and diode germanium based LEDs cannot emit light because they are indirect bandgap materials. So this so said option C. First of all, option C is itself incorrect because it says gallium arsenide is higher than gallium arsenic phosphide. Let's say even if you're talking about option D, there'll be no frequency. You cannot compare the photons which are not even generated. Okay, so these two do not even exist, right? So hence option C or D does not even arise into the picture. They're not valid. These two are not even valid in these expression. You cannot compare two entities of which you can say that they have the photon is not even there, so they have zero energy, but the photon is not there, so I'll not say zero energy photon. Photon is not non-existent. These two entities do not even exist. Hence option C and option D are incorrect by themselves, invalid in this case rather, not even incorrect, invalid. Okay, so that's for this set of problems where we compared indirect versus direct band gap, and second part we saw the dependence on the band gap of the emitted photon. Right, now in this case we have to choose. So this is again a very I remember that almost one of the lectures of the 5 lectures for this week are dedicated to finding the appropriate materials. So I told you one of the appropriate materials, whether it's indirect or direct. Second consideration is what band gap you want to choose. The third, I should say not even more important, but one of the more important, I should say, a rather important facet is the substrate that we are going to make this PN junction on. because remember there has to be some substrate on which all this thing is grown. Okay, so this considers that what substrate do you want to choose. So we have to choose a substrate based on our application and other considerations. So let's do this. So in this for the next two questions, it is asked for us to consider the band gap composition graph of 3,5 compound semiconductors as shown in the figure below. So 3,5 compound, we have already discussed that silicon and germanium, for instance, are group 4 elements, right? But if you combine one group 3 element with group 5 element, you also get semiconductors. So for instance, gallium is a group 3 component. So your group 3 is boron, aluminium, gallium, and indium, and then I'm forgetting the last one. I think the symbol is Te or Tl. Forgetting that. Similarly, for group 5, you have your nitrogen, phosphorus, arsenic, and then I think it's lead or antimony. I don't recall much. But so for instance, you can combine gallium, the group 3 element, with a nitride, it's group 5 element, and you get a semiconductor, gallium nitride, which is a band gap of around 3.4 eV. Similarly, you get gallium from group 3, and you get arsenic from group 5. You get gallium arsenide with band gap of 1.42 eV. And you can just plug and play. For instance, you have gallium phosphide here, aluminum phosphide, aluminum indium phosphide. So there are different ternary or quaternary semiconductors that you can create. Okay, so just I'll spend a bit some more time on to understanding this plot. So it's so on the x-axis what we have is the lattice constants. So lattice constants will depend on the material. So for instance, let's consider gallium arsenide. Gallium arsenide will have a lattice constant of, let's say, 5.65 angstroms. Indium phosphide, which is this dot, will have around, let's say, 5.88 angstroms. Gallium phosphide, on the other hand, will have around 5.45 angstroms, similar to the aluminum phosphide of 5.45 angstroms. And the other lines that you see, for instance, GaX, In1 minus X, this means what we are doing here is it's an alloy of gallium is, let's say, X percentage, then indium will be 100 minus X percentage, or 1 minus X. Gallium is, this X is less than 1. Okay, so because we are changing the mole fraction here, so you can see gallium indium phosphide will switch from indium phosphide to gallium phosphide. You see this line, this dotted line, and this solid line. Dotted line denotes indirect band gap, solid line denotes direct band gap. And please keep in mind, for LEDs we want that devices which are direct band gap. See solid line over here, and the rest you see are just the color. So this is the IR range. You have your range of bluish, orange, yellow, and then red. All right, right. So now let's get into, and on the y-axis, left y-axis is your energy, band gap energy. So again, just to illustrate, your gallium arsenide is, we know, is 1.42, which is over here, and we see gallium phosphide over here, which has the around 2.25, so which is, you can see over here. Okay, so the question asks us that a graduate student wants to fabricate a lattice matched LED. So the first term is lattice matched, emitting near IR wavelength of lambda equal to 870 nanometers. Okay, referring to the data given in the figure, which compound will you suggest them to choose? So first we are given this wavelength, so lambda equal to 870 nanometers, which is 0.87 microns. And if I calculate Eg, remember we can calculate Eg because it should be equal to h nu, so hc by lambda, and we also have this formula 1.24 upon lambda in microns, right? So Eg, what I'll get, just hold on a second, 1.24 divided by 0.87 microns, so this turns out to be 1.425, let's write 1.43 eV. So we want 1.43 eV, and we want lattice matched. Lattice matched means we have some substrate, and the material that we want to grow should be of the should have the same lattice constant. So for instance, if I choose gallium arsenide as the substrate, so I'll do this. First I'd obtain that material Eg should be equal to 1.43 eV. Second thing is that should be lattice matched. Lattice matched means there should not be any difference in the lattice constants between of the two of the if I'm taking, if I'm choosing more than one material, then they should have the same lattice constant. Okay, lattice matched to substrate. So let's just first try to find out where is 1.43 eV. So this is 1.43 eV. So over here, it's this line. Alright, and we see one material which, so it's not actually, let's go somewhere over this because value is 870 nanometers. So we see that the gallium arsenide falls on this line. Gallium arsenide we know has bandgap of 1.42, which is very close to 1.43. And if we choose gallium arsenide as the substrate and we just grow gallium arsenide N type and P type, then we can have this LED which will give us a wavelength, which will emit a wavelength of 870 nanometers upon spontaneous emission. So we choose gallium arsenide as substrate and the material. So here it's the same. So life is much simpler here. You just need gallium arsenide and you will be fine with that. Right? So because we could not, the other thing you can say, okay, I'll choose this material I can choose. But what substrate will you choose? Which substrate will you use to grow this GaX indium 1 - X phosphide alloy, or this, let's say, aluminium indium phosphide alloy? Which substrate will you choose? If you choose indium phosphide as the substrate, right, then you do not have a lattice match condition. See that? Or if you choose gallium arsenide, and there's lot of mismatch. So the best option that we have is we choose gallium arsenide as the substrate and the material for the epitaxial growth itself. Okay. Second problem we have is a similar thing. Again, we need a lattice matched LED with wavelength of 532 nanometers. Okay. So let's just again, as the first step, let's just try to identify what EG corresponds to 532. So I'll do 1.24 over 0.532 because we need to put in micrometers. So what I'll get is 1.24 over 0.532. This comes out to be 2.33. So this is coming out to be 2.33 eV. So we need a material with EG equal to 2.33 eV. So let's draw that line. So this is 2.3, 2.4, so it's somewhere close to this line which I am drawing. The red line that I have drawn, we have to choose a material on this. Second thing, it says that it should be lattice matched. Okay, so let's choose this material, right? An alloy of gallium phosphide and aluminium phosphide. We can see it crosses over at this point and will be fine. It will lattice match to gallium phosphide. There's a problem. You see this dotted line? This is an indirect band gap, so we cannot choose this. In fact, this whole region, you see this grayish region, is of indirect band gap. This is surrounded all by dotted lines. So everything inside this grayish box, a dotted box, is indirect band gap. So we cannot choose anything here, right? So this box is eliminated. The only point that we see here is this. You see this point? It's written 2.33 eV. Direct indirect crossover, and in fact the lambda is given as 532 nanometers. So at the given direct indirect crossover, we try to find substrate, and that too lattice matched. The problem says it has to be lattice matched. If you don't match lattice, there is this stress and there are defects that arise, or otherwise they also arise, but we try to avoid it to the extent possible. That's the idea for LEDs at least. So what we see here is, we are here and we see you drop this vertical line and it perfectly matches with gallium arsenide, right? So we are lucky in this case that this crossover point this point of, what is the alloy? GaX and indium 1 minus XP, right? This fellow. And what is the second line that it's crossing? It's this line, right? This line. So you see, we need to follow this line because the crossover point is here, correct? So what we have, this line corresponds to, so this is gallium indium phosphide and this is aluminium indium phosphide. Okay, so it's a quaternary alloy, and you see it's lattice match with gallium arsenide. So we have find a substrate. So we have gallium arsenide as substrate. But what material is in the epitaxial stack? That is this. So you see this is transitioning, this line that you see, right here, indium concentration is the same, it's 50% they're saying, right? Because the only option that I have is this. I only know that it's a quaternary alloy. So gallium, aluminium, indium phosphide. Again I repeat, this line we have to trace this line, follow this line. This line is starting from here to here. And what are these two lines, this line and this line? These two correspond to aluminium phosphide and indium phosphide. The top line and the bottom line, this fellow, corresponds to gallium phosphide and indium phosphide. Hence these four elements have to be there, right? And what we see here is that X has to be figured out based on the lattice constants that we have. So for instance, here it's 5.65, right? This point is 5.65. It starts from 5.45 to 5.85. So actually indium is exactly 50%. Able to calculate? This is 5.45. This is 5.85. And we are right in the middle of it because lattice match with gallium arsenide. So when it will be between 5.45 and 5.85, when indium concentration, you can see that is the indium concentration that we are changing here, that's 0.5. Hence we do this, and it's a quaternary alloy, so aluminium and gallium will be over here at this point. Hence this is the option. So how do we let me just put it more clearly. It's still causing confusion. We first find out the band gap. So we found out the band gap is 2.33 AV. Fortunately in the question, this itself was written to us, lattice match to gallium arsenide. This alloy that you see is written here, but I told you how to calculate the lattice matching itself. So here it's 5.45, here it's 5.85, and you are right in the middle of it at 5.65. Hence the indium concentration has to be 50%. Second, then you will ask, okay, what will be the concentration of aluminium and gallium? That you can vary. You see this very small region there, it can be varied a bit, or you can see over on this line if you carry on, it can be varied a bit, but not by much, because the total 50% has to be given to indium. The second thing that we found out, it has to be lattice mass to some substrate. The substrates you can see are on the periphery. For instance, aluminium phosphide, gallium arsenide, indium phosphide, and so on. So we just saw that in the question itself. It was very clearly written to us. It's lattice mass to gallium arsenide, and thus we choose this quaternary alloy. Quaternary stands since there are four elements involved here: indium, phosphide, gallium, and aluminum. The problem, the practicality of problem is that when you introduce so many elements, the growth becomes a bit tedious. So for instance, in the first problem that we saw here, it was just gallium arsenide. So you follow the reactants to form the gallium arsenide, optimize the growth process, and you will be fine. This is a much more complicated thing. So it's a bit involved, much more involved than it looks like. But this is a starting point how we do it. Okay, so I'm done with the LEDs part now. For the next I guess how much time is left? For the next 20-25 minutes, we'll be talking about lasers. I do not have much on the lasers. Very few questions are there. It's more of an understanding of the stimulated emission again, and how it's working, how it impacts rather, and how do we utilize stimulated emission for our advantage to create lasers which are coherent, which give out coherent light sources. So I'll pause a bit for this, because from LED's perspective, I guess this is the if you understand this diagram and how we select the materials, you can understand LEDs. And the only aspect that's remaining apart from this is internal quantum efficiency and external quantum efficiency. So if you understand that efficiency part and the choosing the material part, I think there's nothing more in LEDs as far as this course is concerned that you can learn. Okay. So if you have any doubts or comments, just please feel free to ask. Okay, this lattice mask is very important for LEDs. Just please make sure of that. Okay, this is a very this is the simplest of the question that we have done in these 12 sessions. The acronym laser stands for, so it's what we stand for is laser amplification, not attenuation. Okay, it stands for amplification first of all. Sorry, light amplification, not laser amplification. Laser stands for light amplification, so these three options are eliminated by, we know it operates on stimulated emission radiation, so this will be the correct option. How is stimulated, how we extract the maximum out of it, that's the understand that's where theoretical part comes to the picture. This is this. So this is the same, this is from lecture slides again. So what you have is fairly simple thing again. So you have an electron sitting in, let's say, in even state. If you shine light of sufficient energy, in this case h nu we'll assume equal to Eg, the band gap. So you see what will happen is that this electron has left this ground state and got to this excited state E2. Spontaneous emission is on the left side is the original picture. So if you have some, let's say, particle sitting or electron sitting in E2, it and the state available below, so it can drop to E1 where h nu again will be equal to Eg. I'm assuming this to be Eg again. Stimulated or induced emission, what we talked about is that this is some electrons in the excited state, and you shine the light of, again, wavelength equal to Eg. What can happen is that this will act as a catalyst, and what will it do? It will the particle sitting in E2 state will now drop to E1 state. What we will have is you have the original photon that is coming, which is this, and you have another photon h nu, and you can clearly see they have the same frequency, but they're also coherent. So this happens only in case of stimulated emission, not in case of spontaneous emission. Okay. And mathematically, how do I write that? How many particles are there in what state, or electrons for that matter? So let's say there are n2 here in the top excited state, n1 in the ground state, and we had solved we had, remember, we had talked about the Maxwell-Boltzmann distribution. So it applies here. So essentially what we are saying is that n2 should be directly proportional to e to the power minus e2 over kt, and similarly n1 should be directly proportional to exponent of minus e1 over kt. This is the Maxwell-Boltzmann distribution. You take the proportionality constant is the same for both. You take you divide n2 by n1, and you'll end up with something like this, right? And you can clearly see that E2 is greater than E1. That's by definition. This E2 is the excited state, E1 is the ground state. So it appears that in equilibrium, N2 will always be less than N1, right? Because E2 is greater than E1. By definition, E2 is the excited state. So N2 will be less than N1, right? Okay. What this means is that there are more chances for absorption than emission, because you can just understand that this is heavily populated, the ground state, and this excited state is less populated. So the chances, the probability, here we're talking about the probability for absorption will be greater than emission. As it turns out that this is not what we want in laser. We want a lot of photons to be generated, but for that emission has to happen. Forget about stimulated or spontaneous. Emission has to happen. This means the population has to increase in this part. This population has to go up, increase much higher than the population that is over here. Then only emission will be able to dominate the absorption process. That is what is called the population inversion. This means what we require is N2 greater than N1. The excited state population has to be larger than the ground state population, so to speak. Okay, how do we do that? So you see that thermal equilibrium, this is not the case, N2 is less than N1. How do we do that? So we saw one of the things by doing electrical pumping. How? If it's a p-n junction, you supply electrons to n side, you supply holes to p side. Your potential barrier will get lowered, and you'll have a large amount of electrons, right? We have a huge amount of electrons in this excited state, which is what we want, correct? Or you can do by optical pumping. So optical pumping means you shine light, you shine so much light. We solve these kinds of problems when we shine light and we see again your minority carrier diffusion equation comes to the picture, just try to recall that. So what we did a couple of problems there where we had this case that we are shining light on a long piece of silicon, right? And we're shining light only on the edge of silicon, and how does the minority carrier charge profile looks like over time, right? We solve and over length also in steady state. So we solved those kinds of problems before, and those are inherently based. When you shine light, you are going to generate, if the light frequency is more than the band gap, you are going to generate electron hole pairs, and if you are going to generate electron hole pairs, the electrons will be occupying your conduction band, then the population in the excited state, the E2 or the conduction band, will increase, and thus that is called the pumping. That is optical pumping, means you are increasing the concentration or the number of electrons in the excited state by optical means to achieve this population inversion. Because ordinarily, please remember, ordinarily, because system will want to be in the state of lowermost energy, N2 will always be less than N1 at equilibrium. So we have to disturb this equilibrium by either by optical means, that is by shining light, and so that electrons get concentration increase in conduction band, or by electrical pumping. That means you inject electrons and holes, right? So that is a prerequisite step for a laser, for a stimulated emission process. That is necessary but not sufficient. What also we need is that hold on a second. What we also need is this gain to be sustained. So what do I mean by that is that the intensity, right, the intensity of light that is emitted is dependent on I mean, it's not, it's because it's a function of x, so it will dependent on the I naught, which is, let's say, the reference intensity, right? Also it will depend on the gain, it's denoted by gamma. This is also a function of wavelength or the frequency. So this gain, because again please remember that frequencies which are lower than Eg will not even exist, because the band gap has to at least be Eg. The photon is h nu, right, will be Eg, and it's very close to Eg. It's not wide as we saw the FWHM full width at half maxima. Remember that 1.8 kT we saw, delta Eg of 1.8 kT we saw for LEDs. It will not be that wide, right, but it can have some width. Okay, so it again, so that this lambda denotes again the spectral this is dependent on the frequency. We are seeing this symbol again and again, the dependence on frequency. It should happen. So that gain is proportional to N2 minus N1. So once you have population, this gain will sustain. You see this so this is only when this is positive, this gamma is positive, then only your intensity can increase, then only you will achieve something called the amplification. You want more of them. Someone asked in the start, you are injecting, we are bombarding one, we are getting two. Now assume the second state, now you have two photons that are coming, right? What will they do? Each photon now will which can act as the stimulus for an electron, right? If they're high enough N2, right? So these will now create 4. The 4 now then can create 8 photons. Remember how fast it will increase. It increases exponentially rate, right? 8 to 16 and so on. It's an ideal case, but some non-idealities will involve some traps and whatnot. But this is the picture, so it can increase rather fast. This will happen only when this term is positive, the gain is positive, because when the gain is negative, this means if you have, let's say you stop the pumping, optical pumping or electrical pumping, so N2 will become less than N1, because that is at equilibrium. You are removing the stimulus now, external stimulus, the external pumping arrangement. If you are removing, what's going to happen is that N2 will start becoming less than N1, and then you will lose this gain, so amplification will not even happen. Okay, so this is very important. And the third thing which I have not listed here is in lasers is something called a cavity. For more details, I just in the interest of time, I had not included that, but this is essentially that you are confining them to so this is how should I put this, this is something called an oscillation. So when you just remember your LC circuits, only at one particular frequency, right, the signal can sustain. Everything else, it gets damped out. It ceases. Only at what frequency it oscillates. Similar thing happens here. A cavity create cavity in such a case. So just think like this. This is that these are the two ends. Only the so if this length is L, only those frequencies or those wavelengths which are an integral multiple of this lambda, only those can survive. Rest will never survive, right? So there are again modes here. This is more in a bit more involved, but essentially what is happening is that we first ensure that the population inversion is acquired by shining light or by electrical pumping, right? Then which is translated into the gain semiconductor, which is proportional to N2 minus N, and the difference between the population densities there. Thirdly, the cavity is introduced. The role of cavity is just to sustain only one particular frequency or a set of particular frequencies, right? You can go very low in this case. That depends on your L and the integral multiple, right? You can tune your L, you can tune your length so that only specific frequencies, specific wavelengths survive. And that's how what we get is that laser has a much sharper laser. So when we say red laser, it is red laser, unlike let's say when we say green LED is not monochromatic. Lasers are monochromatic to the extent I mean we are touching the theoretical limits there. All right. So this is a problem which is it just encompasses what we had talked about here. That was the theoretical part. Now we come to the application part of it, right? And when we want to make lasers, when we want to fabricate them, how do we do that? So we are given 3 statements. So it says that it is difficult to build a blue laser compared to a red laser, and they say that the reason can be either of these two, because a spontaneous emission becomes stronger with decreasing wavelength and it becomes weaker. So how do we know that? Please remember that there are two mechanisms which are competing always. We saw this in the start of our session today: spontaneous emission and stimulated emission. Both of them have this N2 here and N1 here, right? N2 and N1 densities here, and both are competing for that. N2 is the common term in both of them. It's the constants that determine what's going to happen, right? So what we want is, and this is the relation given between A21 and B21. So B21 is for a stimulated emission, A21 was for a spontaneous emission. And this is the relation. Just look at this relation between A21 and B21. Okay, so what it depends. So what we want is that we want for lasers, we want stimulated emission to be dominant. This implies B21 should be large. Now that's fine, but there's all of them are constants except for this frequency term. So what's going to happen, that as you increase the frequency, right, as frequency increases, right, A21 over B21 increases. The ratio, you bring B21 over here, as a frequency, in fact it's cubic, so it increases much faster, increases much faster. 3 arrows denote, if there's, to denote the cubic influence. So what we see is that at A21 over B21 is increasing. This means spontaneous emission increases rather drastically. Cubic, you can see the effect. Okay, and this is the reason, and now we'll link with this. First let's see S2 and S3. So spontaneous emission becomes stronger with increasing frequency. As we increase the frequency, spontaneous emission increases. Okay, uh, new increases also means wavelength decreases. Okay, so with wavelength decreasing, spontaneous emission becomes stronger. So S3 is false, S2 is true, right? And now compare the wavelengths of red and what is the thing, blue, right? So lambda for blue, let's say it's 300 nanometers, and lambda for red, let's say it's 700 nanometers, right? So there's a factor of 2 here, almost. Let's assume it's to be 2, just for the sake of this discussion. Let's make it 350 then. 350 to 700, it's a factor of 2. This means for spontaneous emission will be 8 times stronger, because 2 cube 8. Spontaneous emission will have 8 times more role to play for blue laser, correct? And thus this makes it, spontaneous emission is more in case of a blue laser, and thus it's difficult to make a blue laser than a red laser. So this statement is also true. Statement 1 is true, statement 2 is true, and statement 2 is the correct explanation for statement 1. Okay, so now let's choose the options. 1, 2, 3 are false. No. 1 and 2 are true. S2 is the correct explanation for S1. This one is correct. This is not, this is not, this is not, and this is not. Yeah, S1 and S2 are true, and S2 is the correct explanation for S1. So this derives from the fact that I'll just summarize that they're competing. Spontaneous and stimulated emission, they're competing. It solely depends on on these constants, the Einstein constants A21 and B21, and we see it's dependent on frequency. So as the frequency increases, spontaneous emission increases, or otherwise you can say that as the wavelength decreases, the spontaneous emission increases. So that makes option 2 correct, and that in turn makes it, because red laser has higher wavelength, so it has higher spontaneous. So sorry, blue laser has 1 second. Yeah, so blue laser has your lower wavelength, right, or a higher frequency, and thus due to this cubic effect, it's much more difficult to fabricate a blue laser. Okay, right. So now I have this last set of problems. Okay, we have 7 minutes, we should be good. So it says, just consider the structures shown in the figure below. So we are given these 3 structures, A, B and C, and I hope that these are called the heterostructures. So remember, when we draw the p-n junction, typically, let's say the p-n junction, so this side was silicon and this side was also silicon. So the band gaps were similar. Remember, both times we see the 1.1 eV as well as for p side as well as for n side, even after the banding, right? These structures what you see over here are called the heterostructures in structure A and B. Heterostructures, by the name hetero, is because they have different band gaps. So so this is an alloy. You can see aluminium, gallium arsenide. This is gallium arsenide, and on this side as well as aluminium, gallium arsenide. Okay, so so this is so this is a heterostructure. Again, this is a heterostructure. Actually, this is okay. Fine. And this is not a heterostructure. This is your simple just a gallium arsenide slab, pure. So what you're saying here, the question asked is refer to the structure A and which of the following statements are correct. Again, more than one option can be correct. So first it asks about the band gaps. Okay, so this is the information. So if you see the structure A, you can see this is the band gap, this is the band diagram that is being drawn. So we know gallium arsenide has around 1.4 ev, 1.42, which is 1.4 ev, and this is clearly looking larger than that. So whatever this Eg2 is, it is greater than 1.4 ev clearly. So what we see is that the band gap of gallium arsenide is smaller than the band gap of aluminum gallium arsenide. So this is correct. This option is correct. Second thing is the refractive index. So what it's typical thing that you can try to remember is that the refractive index ordinarily, this is not a is just inversely proportional to your Eg. So the higher the band gap, the lower the refractive index. Okay, so in this case what we'll have is that the refractive index of gallium arsenide, so band gap of gallium arsenide is lower, which we have established. So the refractive index of gallium arsenide will be higher. So that's it. So we just as I told you, these are called these entities are called heterostructures because the materials that you see here, they do not have the same band gap. So this is what is known as a homostructure. This, the PN silicon diode that you see, this is a homostructure. Okay, and then we see from the diagram itself we can find the band gap, and we know refractive index is inverse of band gap. So with that we establish the refractive index as well as the band gap of for the structure A. Okay, same thing is asked. Now it is being asked that which one will you prefer fabricating a gallium arsenide laser and why. Okay, so please remember that laser, what we so remember there are two states that we have, the excited state and the ground state. Okay, so it just so happens that when you have such kind of a configuration where you have on the left you have a higher band gap material, in the middle you have a lower band gap, and again on the right you have higher band gap. So what can happen, you just think of it as a quantum well. So electrons can easily come here, right? This will get, how they get filled, that's a different thing, but if they get filled, it's not readily a path is not readily available to be escaped. So what's going to happen is that you can have high population of electrons in this case, in these structures, right? This is not possible here in structure B or in structure C. Okay, structure C, it's possible only in these kinds of structures where a well kind of creation is formed, and this is actually a quantum well. So this is not an exaggeration that I'm saying, this is just a much more simplified version of a quantum well, but this is a quantum well, not infinite obviously, because this, you can see this finite edge over here. Okay, so this is confining the electrons, right? The second thing that it's also doing is also confining the phonons. Okay, sorry, not phonons, what I'm saying, it's also confining the photons, right? How it's confining the photons? So let's say a 1.4 ev photon is generated, right? It cannot interact with this. Remember, this has higher energy. Let's say for the sake of discussion, let's say it's 1.7 ev. So 1.4 ev will have no impact on this 1.7 ev structure. So all the photons that are 1.4 ev, they will interact only here. They'll get reflected from elsewhere if you have reflective coating, but they'll interact only here. They can, so all the energy that is being, all the photons that are being released when the electrons are dropping down from here, it will be amplified much better in this case, because all this 1.4 ev will only be confined, will only be available for the gallium arsenide material, not other materials. Okay, which is not the case here. So for instance, if you create a structure, if you shine light here, and let's say your active material is only this much, right? But a photon can escape here, and it can cause the emission or maybe the absorption here, which is inefficient. We don't want that. We want it to be confined. Hence, so what we see is that the electrons are confined due to the band gap, the heterostructure, and the photons are confined due to the fact that there's a difference in band gap. So the photons are available only for this gallium arsenide fellow. Okay, electrons will not be confined here. You can see that, in fact, this is not even possible because aluminum gallium arsenide has a higher band gap. But in principle, you can see material X and material Y, electrons will not be confined here, right? So and neither will the photons. So photons will be here, let's say, or here, not here. So structure A, because it confines both electrons and photons, yes, being a double heterostructure. This kind of so if we talk about only in terms of your band gap difference, then we call it as heterostructure. But this fellow is structure A is confining electrons as well as photons. Thus it is referred to as a double heterostructure. Okay, so that is all, I think, for today's session. We are on time. It's 5 o'clock. And please remember, next week there will be a revision session. If you are interested, I'll highly recommend, if you have any doubts, just please send them, either numericals or conceptual. Otherwise, I'll prepare a 1 hour presentation, just taking the important topics that I feel should be revised.